Okay, hello everyone. From today, we will learn about multivariate probability distributions. The chapter 4.1 is introduction for the multivariate probability distribution, and here we give two examples. The first example of multivariate probability distribution is observing the number of animals surviving in a litter is concerned about the intersecting of these two events. The first event is the litter contains n animals, and the event B is y animals survive. So the number contained in the litter there could be one variable, and the how many of them survives can be the second variable. So we can make this as multivariate. We can define multivariate probability distribution on this type of events. Or also, this is first example. The second example would be observing both the height and the weight of an individual. The height for the height and weight, x1 and x2, for the given individual could be the multivariate. This would follow some distribution, multivariate distribution or something. Okay, so here are two examples of multivariate probability distributions, and let's look at more details in the later slide. In chapter 5.2 is about bivariate and multivariate probability distributions. Let's look at definition 5.1. Let y1 and y2 be discrete random variables. The joint probability function for y1 and y2 is given by py1, py2, which is probability of y1 is value y1, and the random variable y2 is value y2. Uh, so we can define the uh, joint bivariate probability function like this for the discrete random variable case. Okay, for the example, the y1 could be the number of dots appearing on die 1, and the random variable y2 is the number of dots appearing on die 2. So there's two dices. Here's die 1 and here's die 2. And y1 is related to the first die, and y2 is related to the second die. And the probability distribution for y1 and y2 can be defined like this. Probability of the first dice have value of small y1, and the probability of die 2 have the value y2. And actually, these two events are independent. When we are flipping the dice, the result of y1 do not change the result of y2. So those two events are independent. So actually, this is the when the probabilities when the events are independent, this is probability of this thing times probability of that thing, which is 1 over 6 times 1 over 6, which is 1 over 36. And with graph, we can represent the probability related to y1 and y2 like this. So here's this axis is for y1, and this axis is for y2. And for each of y1 and y2 axis, we can have the value 1 to 6, 1 to 6, and for each combination, the probability is 1 over 36. So 1 over 36. Okay. And here is theorem 5.1. If y1 and y2 are discrete random variables with probability function p y1 and y2, then first, p y1 and y2 is greater than or equal to 0 for all y1 and y2. And second, sum of all p of y1 and y2 equal to 1, where the sum is over all values of y1 and y2 that are assigned non-zero probabilities. And actually, these properties are from axiom of probability, axiom of probability. So the set space S, there is space S, and all the events, all the simple events are called E1 dot dot dot, let's say E1, E2, and so on. Then P of EI should be greater than or equal to 0, and P of all the events, which is 1. And from this axiom of the probability, we can check this should be the true. And we also checked similar theorem for the discrete and continuous random variable case. And so this is kind of general extension for the joint probability function case. Okay. Let's check example 5.1. A local supermarket um, has three checkout counters. Two customers arrive at the counters at different times when the counters are serving no other customers. Each customer chooses a counter at random, independently of the other. Okay, and let Y1 denotes the number of customers who choose counter 1, and Y2 the number who select counter 2. Find the joint probability function of y1 and y2. Okay, so here two customers arrive at different time points, and there are um, no serving cost, no other customers, and these two customers choose a counter independently. So there's three counters, three checkout counters, counter 1, 2, 3, and there's two customers, customer A and B, and they randomly select 1 or 2. So sample point probably could be 1, 1, or 1, 2, 1, 3, and 2, 1, 2, 2, 2, 3, and all the possible cases, which is for A, we can choose 3. For B, we can choose 3, which is 3 times 3 is 9. Okay, so we have 9 possibilities. Which are these? We can list all of them. Okay. And here, let y1 denote the number of customers who choose counter 1. Okay, so how many choose 1? So y1, in this case, y1 equals 2 and y2 equals 0. What about this case? Y1 is 1, y2 is 1. What about this case? Y1 is 1 and y2 is 0. So in the similar way, you can check the random variable for the event, and then after that, you can construct your probability distribution. So here, this part is y1 equals something 0, 1, 2, and this part is for y2 0, 1, 2, and the each are equally likely. So all the events here are equally likely. The probability for each event is 1 over 9. And what's the 0, 0? What's the case for 0, 0? And that is this one. Here, this one, y1 is 0, y2 is 0. So it is 1 over 9, 1 over 9. And let's make it work. Okay, so wait. Uh, okay, now it is working. Okay, for this one, it is y1 is 1, y2 is 1. For this one, y1 is 0, y2 is 2. For this one, y1 is 0, y2 is 1. For this one, y1 is 1, y2 is 0, y1 is 0, y2 is 1. So for 0, 1, 0, 1, here we have 0, 1. Here we have another 0, 1. So 2 over 9 here. How many of we have 0, 2? 0, 2 is here. It is 1 over 9. And what about 1, 0? Maybe 2. 1, 0 here, here. Yeah, so 2 over 9. What about 1 and 1? We have 1 and 1 here, 1 and 1 here. And also yeah, maybe that's all. So it is 2 over 9. What about 1, 2? No 1, 2. It should be 0 and 0. And here this should be 1 over 9. And 2, 2 is 0. So let's check whether the sum of everything is equal to 1. 1, 2, 4, 6, 7, 8, 9. Okay, so the joint probability function of y1 and y2 is this one. So p of y1, y2 is the probability table is given here. Okay. Let's look at definition 5.2. For any random variables y1 and y2, the joint bivariate distribution function fy1 and y2 is defined like this. Okay, this is definition, and actually this is extended definition for distribution function. So for example, fy, this is probability of y is less than or equal to y. So this should be the natural extension for this. Okay, let's solve the example 5.2. Um, consider the random variable y1 and y2 of example 5.1. Okay, so the probability table for example 5.1 is given here, and find f minus 1 comma 2 and f minus 1 f 1.5 comma 2 and f 5 comma 7. Okay, so what is f minus 1 comma 2, and this is probability of y2 is less than y1 is less than or equal to minus 1, and y2 is less than or equal to 2. About this one, this is end, and there is no event that have negative for the event y1. So there's no event that have minus negative. So the probability for this, there is no event um, uh, for this. So this one should be 0. Nothing is in the set is for the set here. And what about f 1.5, 2, which is probability of y1 is less than or equal to 1.5, y2 is less than or equal to 2. For this one, 0, 0 is inside of here. Y1 is this one. Okay, so all the events here. Y1 is less than or equal to 1.5, and Y2 is less than or equal to 2. So sum of all these probabilities, which is 8 over 9. What about F 5.7, which is probability of y1 is less than or equal to 5 and y2 is less than or equal to 7. And actually this contains everything. Y1 is less than or equal to 5 and y2 is less than or equal to 7. All these things, which is everything. So the probability is 1. Okay. Definition. Let's move on to definition 5.3. Let y1 and y2 be continuous random variables with joint distribution function f y1, y2 if there exists a non-negative function f y1, y2 such that this thing holds for all y1 and y2, then y1 and y2 are said to be jointly continuous random variables, and the function f y1, y2 is called the joint probability density function. Okay, so here this is extension of the joint probability density function for continuous random variable case. You recall that fy is equal to minus infinity to y f t dt. Then you can find that this is the kind of general extension from the univariate density function. So for the univariate case, it's like that. So density function is like here, and f of y is the area to here. If this is y, then f of y is the area of here when this is fy. Okay. And in this bivariate case, we have distribution function defined on the two-dimensional space, and the f of y1, y2 is actually this axis is y1, this axis is y2. The value y1 and value y2 is here. Then the area of something here is the probability of f of y1, y2. The volume, if we look at the y1 and y2 like this, y1 and y2, 0 to plus sign, and the area of these that determines the distribution function f y1 and y2. Okay. And theorem 5.2 says about these. If y1 and y2 are random variables with joint distribution function f y1 and y2, then number one, f negative infinity comma negative infinity is equal to f negative infinity comma y2 is equal to f y1 comma negative infinity equals 0. So what it says is that if any of components is minus negative, then the distribution function have is 0, and second, f infinity comma infinity is 1, and also if y1 star is greater than or equal to y1, and y2 star is greater than or equal to y2, then the uh, this thing is greater than or equal to 0. And actually, what this means is that um, so if this is y1 and if this is y2, and then and if we have the density defined on okay, let's say these are star and these are y1 and y2. Okay, so Fy1 star comma Fy2 star is the volume defined on the set here, and uh, Fy1 comma Y2 is the volume defined in here. And so if you take and also this one y1 star and y2, the area is here, and the area for this one is here. So if this one if this one minus this one minus this one plus this one, it is actually area defined on a volume defined on this one, a volume defined on this one. So since the joint density function is actually always greater than or equal to 0, so the integrating it from y1 to y1 star and y2 to y2 star from y1 comma y2, the t1 t1 the t2 t1 t2 okay, t1 t2 okay. So let's say this axis is t1 and another axis is t2. Okay, then this integration should be greater than or equal to 0, so that's the property number 3. Okay. Okay, let's move on to theorem 5.2. If y1 and y2 are jointly continuous random variables with a joint density function given by f y1, y2, then the number 1, f y1, y2 is greater than or equal to 0 for all y1, y2, and second, integrating the joint density function from minus infinity to infinity is 1. And actually this theorem 5.2 is also general extension from the axiom of probability, and for the bivariate density function fy1 y2, we can visualize it like this. And here the area here stands for So integration of a1 to a1 to a2, integration from b1 to b2, f y1 comma y2, dy1 dy2. Let's look dy1 y1 a dy2 dy1. Okay, dy2 dy1, and this is same as the probability of y1 is from a1 to a2, comma b1 y2 is from b1 to b2. Okay. Okay. Okay, let's move on to example 5.3. Suppose that radioactive particle is randomly located in a square with size of unit length. Okay, so radioactive particle is randomly located in a square with side of unit length 1 and 1. That is, if two regions within the unit square and of equal area are considered, the particle is equally likely to be in either region. Okay, and let y1 and y2 denote the coordinates of the particle's location. Okay, so let y1 and y2 denotes the location for the particle, and a reasonable model for the reactive frequency histogram for y1 and y2 is the bivariate analogous of the univariate uniform density function on the interval here. Number A, sketch the probability density surface. Okay, so the probability density surface. So here, the probability is defined on unit square here. Let's say this is y1, this is y2. Then the probability defined on this interval should be 1, 1, so that the volume of this is 1. Okay. This is 1. Okay. So this is the density function for bivariate random variable. And what about number B? Find f 0.2, 0.4. So f 0.2, 0.4 is actually probability of y1 is less than or equal to 0.2, comma y2 is less than or equal to 0.4, and actually y1 is less than 0.2, 0.4, this one 0.2, 0.4. The probability is the volume here, so it's like volume here, volume of this box, which is 0.2 times 0.4 times 1, which is 0.08. So this is f 0.2, 0.4, and actually the figure 5.3 describes the situation. Since my graph is not very good, I will replace it with this. So this is our probability density surface, and f 0.2, 0.4 is that here's 0.2, here's 0.4, and the area corresponding to this region is here. So the volume of this rectangle is 0.2 times 0.4 times 1. It is 0.08. Okay, and what about the problem C? probability of point 0.1 greater than y1 is 0.3, comma 0.2, y2 0.5, and the length in the interval y1 is zero point 0.2. Length in the interval y2 is 0.5. So this is 0.2 times 0.5 times 1. The rectangle, the volume of the rectangle is this one, which is 0.1. Okay. Okay, let's move on to example 5.4. Gasoline is to be stocked in a bulk tank once at the beginning of each week and then sold to individual customers. Let Y1 denote the proportion of the capacity of the bulk tank that is available after the tank is stocked at the beginning of the week. Okay. Because of the limited supplies, Y1 varies from week to week. Let Y2 denote the proportion of the capacity of the bulk tank that is sold during the week. So Y2 is the that is sold during the week. So Y2 should be less than Y1. So Y2 should be less than Y1. And because y1 and y2 are both proportions, both variables take on values between 0 and 1. Further, the amount sold y2 cannot exceed the amount available y1. Okay, this is equation. Suppose that the joint density function for y1 and y2 is given by here. A sketch of this function is given in figure 5.4, which is this one. So the joint density function is defined like this, and find the probability that less than one half of the tank will be stocked. Less than one half of the tank will be stocked, which is y1 is less than 0.5. And more than one quarter of the tank will be sold. So Y2 is greater than or equal to one quarter, 1 over 4. And this shouldn't exceed Y1. Anyway, the Y2 is greater than or equal to 1 over 4 and less than Y1. Okay. So we want to find the probability of this. So what we want to calculate is probability of y1 is less than or equal to 0.5 and y2 is greater than or equal to 1 over 4. This is what we want to calculate. Okay. To calculate the probability of this, so y1 is between 0 and 1 over 2, and y2 is greater than or equal to 1 over 4. It's actually, you can integrate the area, the, you can integrate the area in this interval for joint density function. So it's double integration, and we have joint distribution function which is 3y1 and dy1 dy2, and from here the probability is defined on this area. So the integration is for part of y2. Y2 is going from 1 over 4 to 1 over 2. So 1 over 4 to 1 over 2. And what about y1? Y1 moves from here to here. So it is from y2 to y2 to 1 over 2. Okay, so let's integrate this and 1 over 2, 1 over 4, and if we integrate it with respect to y1, it is 3 over 2 y1 squared, and y1 is from y2 to 1 over 2 dy2, and this part is 3 over 2 1 over 2 squared minus 3 over 2 y2 squared. Okay, and it is 3 over 8. Okay, and so this part becomes 3 over 8 y2 minus 1 over 2 y2 third, and y2 is from 1 over 4 to 1 over 2, and so this is 3 over 16 minus 1 over 2, 1 over and minus 3 over 8, 1 over 4, minus 1 over 2, 1 over 4 third. So if you calculate this number, you will get the answer for the probability of this interval. Okay. Okay, so far we have learned how to calculate probability of the intersection of two events, y1 and y2, for the discrete and continuous cases. We can extend it to calculate probability of the intersection of multiple events. The theorems described in the slides that can be extended to multiple events, intersection of multiple events. So for the discrete case, we can specify the probability of multiple events py1 to yn as this one. And for the continuous case, the distribution function f of y1 to fyn can be specified as something like this. Okay, so that's it. And homework problem for chapter 5.2 are these. Okay, chapter 5.3 is about marginal and conditional probability distribution. This definition 5.4 describe about marginal distribution. So let y1 and y2 be jointly discrete random variables with probability function py1 and y2. Then the marginal probability function of y1 and y2 respectively are given by below. So the marginal probability function for y1 is this. P1 y1 is actually sum of all the p of y1 and y2 with respect to y2. So here let's say it's like this. So here's probability table for y1 and for y2. If and here we have probabilities, and if we sum the probabilities over this way, if we sum up the probabilities this way, so sum up the probabilities over y2, then we get the probability of this with respect to y1 equals something. So this is one probability of a p of y1. If we sum up all the probability that related to y2, if we sum up this way, then we can get the p1 y1. This is this one. And what about p2 y2? if we summing up probabilities this way, then we can calculate P2 Y2. If we summing up all the probabilities related to Y1 for each of Y2, we get the marginal probability function for Y2. Okay, that is for the discrete random variable case. And let y1 and y2 be jointly continuous random variables with joint density function fy1 and y2. Then the marginal distribution function of y1 and y2 respectively are given by these. So f1, y1, we integrate with respect to y2, or if we integrate with respect to y1, we can get the marginal density function for y1 and y2 respectively. Okay. Okay, let's look at the example 5.5. Um, from a group of 3 Republicans, 2 Democrats, and 1 Independent, a committee of 2 people is to be randomly selected. Let y1 denote the number of Republicans and y2 denote the number of Democrats on the committee. Find the joint probability function for y1, y2. Okay, probability of y1 is small y1, comma, probability of y2 is small y2. This is the situation is there's 3 Republicans, 2 Democrats, and 1 Independent, and so the situation is we are choosing 6 choose 2, committee of 2 people, 6 choose 2, and among them we want to select among 3 we want to select y1 number of um, Republicans, and we are choosing 2 among y2 number of Democrats, and 1 choose something which is actually uh, uh, if we know y1 and y2, yeah, actually we can know if y1 plus y2 is 2, then uh, is 2, then this number is 0. If y1 plus y2 is 1, then this is 1. So um, so we can say 2 minus so here is 2 minus y1 minus y2. If we specify like this, then um, this should be okay. Okay, and find the joint probability function of y1 and y2, and then find the marginal probability function of y1. Okay, so for y1, the y1 can get the value of 0 or 2, 0 or 2, and for y2 also 0 or 1. 0 or 1 or 2. 0 or 1 or 2. Okay. But this one cannot be 2 if y1 and y2 are both anyway, let's just calculate. Okay. For both y1 and y2 get a 0, that's not likely because we cannot pick 2 from independent group, so this probability is 0. And what about we pick y1 equals 1, 3, 1, 2, 0, 1, 1, 6, choose 2 is 6, 5, 2, 1, 15, 15, 3 times 3, 3 over 15. So here is 3 over 15. Here y1 is 2. 3 choose 2. 2 choose 0. 1 choose 0, which is again 3 over 15. For this one, 3 choose 0. 2 choose 1, 1 choose 1, which is 2 over 15, and here 1, 1, 6 over 15, 1 and 2, 1 and 2, it's impossible, so we are with the probability 0, and 2 and 0, 2 and 0, y2 is 2, 3, 0, 2, 2, 1, 1, this is 1 over 15, and 2, 0, they are 0. So this is the probability table. Let's sum all the probabilities. 3, 6, 12, 14. Yes, yes, correct. So we have the table, we have the right table, and find joint probability function. So we found the joint probability function, and then find the marginal probability function of y1. So we sum the probability to this side, and total 3 over 15, 9 over 15, 3 over 15, which is 1 over 5, 3 over 5, 1 over 5. So this is the marginal probability. So for y1 is equal to 0, 1, 2. Probability of y1 is 1 over 5, 3 over 5, and 1 over 5. Okay. Now let's move on to example 5.6. Let f y1, comma y2 is defined like this, and sketch f y1 and y2, and find marginal density function for y1 and y2. And the sketch is on figure 5.6. So the density function defined on this region. For y1, it is defined on from 0 to 1. For y2, it is defined on 0 to 1. And to calculate the density function for y1, we can integrate it with respect to y2. So integrating with respect to y2, which is f y1, y2, dy2, and y2 is from 0 to 1, 0 to 1, then we can calculate f of y1. Okay, so to calculate this, we can integrate from 0 to 1 to y1 dy2, and actually this is from 0 to 1 to y1 y2. Okay, to y1 y2 from 0 to 1, and this is 2y1 minus also 2y1. Okay, so f of y1 is 2y1, and on from 0 to y1 is 1. Okay, this one. And for the y2, for fy2, this is from 0 to 1, fy1, comma y2, dy1. And I will leave it to you students, so I think you can calculate it by yourself and check the result with the answer sheet from the textbook. Okay. And thank you and see you next week.